Alright, we will start our today webinars. The titles is Solve Heat Transfers Challenges on Electronics Box using the smart ways. So I'm William, so I will be the presenters for today. So this webinar will approximately take about 1 hour or maybe less than that, depends on the progress. So what we will bring you through is that we will bring you through a couple of introductions and then some case studies, and eventually we'll close up with summaries. And without further ado, so let us move forward to talk about these particular webinars and get started. So first of all, we are ATE. So what we provide is that we provide engineering solutions. Our purpose is to empower local engineers and companies to meet engineering challenges through advanced technologies and enterprise. Our vision is to be recognized by customers and industries as one of the leading 3D engineering solutions provider in ASEAN. So we have offices includes in Malaysia and also in Singapore, in Penang, Kuala Lumpur, Johor, and Singapore is our headquarters. So we are still growing, and our customer is our assets that helps to keep us grow. Okay, I saw some message. Everyone can hear me? Anyone else that cannot hear me? Okay. Let me just continue. We want to be a valuable partners to your businesses to transform, empower, and protect your interests in the market. So today agendas, we will go through an introductions and then a case studies with actual examples, and then we have a summaries to summarize the whole what have we have talked about today. So under introductions, solving heat transfer challenges. What we have here, we will understand that modern electronic equipments nowadays range from toys, appliances, IoT, or even high-power computers. So all these, the reliabilities and the performance of the reliabilities of the electronic components are highly related to the temperatures of these particular components and equipment itself. The reason because of the electronics current that passing through these particular electronic components will causes them to become a hot spots, and then these particular hot spot and temperatures, high temperatures, will jeopardize its safety and reliabilities. So the failure rates will increase exponentially with temperatures. As the temperature increase, the failure rates will also increase as well. So and hence the efficiencies of the thermal control in these in the operations during the operations of electronic equipment is important. So what we are focusing on is we want to know how we can validate the effects of temperatures in the electronics boxes or electronic components, and then we have heat transfers effectiveness. We want to know about how effective is the heat transfers and heat being released away from the system. And of course, one of the important things in CFD is that the ventilations in an electronic cooling systems is important as well. How does the ventilation in the fluid regions, and how does that particular ventilations carry away the heat from the heat source? So we have roughly talked about the introductions, and then now we will go into the case study itself. Today I have prepared 3 case studies. The first case studies is LED lights, which is on the left-hand side, the pictures on the left-hand side. Then we have a power supplies, electronics box, and we also have another electronics box as well. Then Example 2 and example 3 are pretty much similar. So we will go deep into how does that being validated in this case. So let's go into looking at the first examples, which is the LED lights case studies. So these LED lights are designed to fit into a conventional light socket with the sockets on the end and LED bulbs on the front. So it designs with 12 LEDs on the PCB boards, and there are openings on the sides of the LED bulbs for air to pass through it. So the heat sinks will be the core components to dissipate away the heat. So each LED generated 0.5 volts in this case, and we will go into understanding it by looking at the models itself. So what we have here is a models which we are shown in the slides. So these particular models are consist of 12 LEDs and attached to the PCB boards. So going through section views, so we'll look at the inside components. So these models have been simplified, remaining only the PCB boards together with the heat sinks and openings for the air to release away and cooling the systems itself. So some of the assignments are included on the boundary conditions. Just quickly go through these. We will focus more on the results portions on how do we capture the information from these particular studies. So there are materials that we have assigned in each of the components inside, and then including it, we have the some of the material assignments and the boundary condition assignments as the thermals and the resistance there. Then for each of them are the heat source where we assign, as we mentioned, each of the LED lights LED chips will produce a 0.5 volts heat source to it. So, and then what we will do here is that we will, when we're running the studies, we will look into a couple of informations, which is the temperature plots of each of the bulbs as well. So let's go into understanding how the results of these particular studies. So first of all, what we will look at the temperature plots of the studies. So if you look at it, after we have run through the studies with the boundary conditions assigned, we will get a temperature plots and certain goal informations. So let's say if you are interested in getting to know the temperatures and how does the temperatures build up in the systems. So you will notice that at the end of the studies, this is the maximum temperatures of the studies. And we can also look at how does the temperatures being built up as iterations goes by. And with a starting temperatures of around 60 plus, and it builds up as it goes by when the 0.5 heat source generated the heat, and at the same time when the coolings are taking effects, and when it reaches the steady states, so you will see that the temperatures started to converge. So we might be interested in knowing how does the heat sinks performs as well. So we can also show the results of the heat sinks and how does the temperatures being built up across the sessions. So from here, what we will see is that at the initial temperatures of 35, and as the heat goes by and the heat sinks will release away temperatures and eventually reaches a temperatures of 55. So of course, when you are doing these kind of studies, you will definitely have some a failure criteria or a certain goals or objective of the temperatures for you to reach, for you to achieve. So different color plots will be able to, we will be able to prop out some of the informations in the prop to understand what is the temperatures difference inside the heat sink itself, and also on the outsides of the plots. So getting the studies is pretty much simple. What we want to know now is that once we have get the results and so on, the important thing here is about optimizations and optimizing your particular results to achieve a particular temperatures that you require. If, for example, in this case, if 64 or 64 degrees is something that is beyond the working temperatures of your particular components, what you need to do is that you want to redesign your heat sinks or even reduce the light bulbs to get a better results or lower temperatures. So what you need to do is you do not need to go through the difference. Do not need to go through by duplicating the models, duplicating the results again to get it done. So what we can do is that we can utilizing the particular the parametric study. So what we are wearing here is that we are wearing the circular patterns, the number of fins of 20 to 40, 60 and 80s and 100s here. So what we need to do here is basically keying in all the values of the fins patterning, and then what are the parameters that you want to monitor. For example, here is all the LEDs temperatures, and then it will generate different scenarios and run everything accordingly, and then eventually it will give you all the different models where you have uh, more fins, 40 fins, and then you have 60 fins, and then more 80s, and eventually 100 fins. So from here, we would like to interpret the result. So at 20 fins, we have a maximum temperatures of around 91. So when we have a 40 fins, you get a slightly lower maximum temperatures. So 60 fins, you get 89, 80, 90s, and 92s. So from what we have here is that we understand from these particular models, with more fins or more number of fins doesn't mean that the heatings are better. Okay, you increase the numbers of fins, increase the number of areas for the heat to dissipate away. But what happened here is that the ventilations might not be good when you have too many fins blocking the airway. And bear in mind that what we have here is all purely on natural convections. There are no fan blowings or no forced convections in the systems. So a good way to understand these particular ventilations will be looking at the flow trajectories. So let's just look at these flow trajectories. So for better clarities, so what we have here is we will be able to notice and understand how does the flow go through during these natural convection scenarios. So if you would like to have some more inside view, we can section it and seeing how does all the airs flow through and with different indicators. It can be velocities, it can even be the temperatures plot as well. And we can go change the how does it being represented. Make it slightly smaller. So we can also understand how are there any recirculations in the systems and so forth. So these particular studies, we are focusing more on natural convections and letting letting the models and letting the heat sinks cool down the systems by itself using natural convections. And what we are looking at is we also go through some parametric studies to go through different design scenarios. In this case, geometrical alterings, geometrical iterations for different sizes, different number of fins in the systems to understand whether the effectiveness of the cooling. You're also understanding the ventilations in the system to see are there any recirculations or are there all the flows are flowing out. We are able to release away from these particular openings and release from this exit in the models. So if we go back to our slides, so the maximum temperatures on the initial studies is 64. So we want to know how does the heat sinks design affected the cooling performance. Hence, we have run through some parametric studies to vary the number of fins from 20, 40, 60, 80s, and eventually get 100s. So we understand that the more the fins is, doesn't mean that the cooling or the heat dissipated effectively. So from these particular studies, we understand that the best studies here is actually a 40 numbers of fins. So the next examples we have here is power supply examples. So this is no longer only a natural convection case. So this also included the forced convections where fans comes in. So in this case, our objective here is to make sure that the maximum allowable temperatures is 100 degrees C. So we will need to go through some configurations here. The first configurations is number of fans in the system. Probably the positions of the fans can affect the cooling as well. Different types of heat sinks and how it will affect the whole system as well. So let's look into the models again. So in these examples, it's a slightly complicated examples compared to the natural convections we have in the LED bulbs. We have a couple of configurations here, including the fan positions, two fan scenarios, different heat sinks scenarios, pin type heat sinks, or a small pins, low height pins type design. So what we are really looking at is understanding what will be the as we have a objective of 100 degrees C temperatures. We want to achieve that. We want to make sure that everything's are below that temperatures. So of course, just quickly go through the boundary condition setting up, which includes the materials selections and the material assignments in the system. Then we have openings to the environments, and we have fans, fan data curve that we assign to the external fans inside the system. And then there are heat sources on the chips, on the PCBs, on different components as well. And then we have a couple of goals to use for convergence, including the temperatures of the solids from between these two solids, because this is where we are focusing on, and the temperature should not exceed hundreds. So let's go into the results and understand what happens in the system. So of course, nothing new here. We are able to call out the temperature plots to understand what will be the temperature of the fluids and the solids inside. We can basically understand it by letting it going across the different regions and looking at the how does the temperatures changes across different layers from heat sources to heat sinks, and you'll notice that the temperatures plot changes accordingly. And we notice that the highest temperature is 124. So, but however, these are not our main objective. Our main objectives will be looking at the goal plots. As I mentioned earlier, we would like to achieve the temperatures of hundreds, and we want to keep it below hundreds. So all we have here is a temperatures of 130 plus. So this basically have is a cases where we did not achieve our objective of 100 degrees C on the two chips. So to understand further on how we can optimize the models, we will need to look into a couple of things, including how does the ventilations goes by in the system. So if you do some animations of the flows, so you will notice that, okay, there are a couple of ventilations going through this and exceeding the fans. So the fans serve as suctions to suck out the ambient air from the outlets, from the ambient conditions, from the atmospheric assignment that we have put in earlier. And then cool air go through the systems and cool down on the heat sinks and exceeding the system. So let's go into understanding if what will happen if we have a different two fans scenarios. So we are working on heat sink 3 earlier. So let's look at two fans heat sinks scenarios with heat sink 3 scenarios. So let's load up the results. And again, we can straight away go into and looking at the results of the fans. So what we notice here is that there is a decrease in the temperatures. What we have here, instead of 130 plus, we now have around 109 and 117 temperatures degrees C here. So this still doesn't achieve our objective of 100 degrees C. So what we can do here is we can go back and try to understand what will happen if we are using a different types of heat sinks. One fan, okay. So one fan scenarios with a different positions. And quickly go through it again, looking at the results. And the temperatures are slightly lower with the new positions, but still it does not achieve the temperatures objective that we require. So the workflows here is that you get the results and then you go through different studies, adding in different scenarios. Now we use the different types of fan studies and so forth, and then look at how does it goes by again and again. So with different iterations. So let's look at different types of heat sinks, and with the two fan scenarios, what will happen. So if you look at the results plots again, so what we have here is, yes, these particular studies kind of achieve our scenarios, our objective of below 100 degrees or maximum of 100 degrees temperatures, which it is still below the parameters that we want to achieve. So let's look at the one last cases, which is one fan of a heat sink one. And let's look at the results plot. And the results shows that the maximum temperatures are around 102, 103. So I can say that these particular studies are also very similar or very close to our objective. Design criteria will come into considerations. of decisions of whether you to use one fan or two fans in the systems. So of course, if you use one fan, it will be slightly lower costs, and at the same time, you also achieve that a lower noise in the system. And if you're using two fans, it will be you will have a lot more noise comparing to these systems. So we go through the variables of having one fan, two fans, different heat sinks design in the systems to achieve the results of 100 degrees C uh, in our to achieve the objective of 100 degrees C. So to understand better, let's go back to the slides and consolidate and do a summarize of what we have done. So we have a power supply design, and we want to decide for the best design parameters of achieving of maximum allowable temperatures of 100 degrees C. So the variable things that we can do here is the number of fans required, whether it's a one fan or two fans. We can even position the fans in different locations to see the heat releasing performance. And then we want to also determine which is the best heat sinks design in the system. So what we have gone through, original designs, running the studies, cutting the temperature plots and the flow trajectories. Then we add up additional fans to see whether the temperatures are being decreased after the studies. And we also varies between different heat sinks design. And as for the results, what we have is we go through two fans with three different design, lower pins one, taller pins, and the fins design. So what we have achieved is that with these particular designs, we managed to with the third iterations, with the third scenarios, we managed to achieve 100 degrees lower than 100 degrees C. But due to the considerations of the noise in the systems, we reduce it to one fan, and we achieve 102 and 103 degrees C in at maximum temperatures. So from there, we will be able to decide how many fans to use and which types of heat sinks that we require in calculating in this particular power supply design. So next up, we will look at the one last examples of today. So again, this is very similar cases to the previous examples of the power supplies. So in this case, we want to understand the cooling differences between the internal fans or external fans of electronics box, and the decisions are made to whether to use internal or external fans. And of course, the different heat sinks designs as well, and to look at how would it affect the overall cooling. So let's look at the model itself. So in this case, we do not assign any design criteria. This can be the initial states of your designs to understand what is the temperature difference between what is the temperatures of the overall systems, and to get a better understanding. So I would like to go a little bit deeper in understanding these particular models. So let's look at it from the section view. So what we have here is that we have different boards across it. So the main PCB boards that carries all the chips, capacitors, and different electronic components. And then we have additional boards that carries chips on it. And then there are more components on top with will generated heat into the systems. So, and then in this case, we will use the internal fans and assigning outlets, inlet and outlets on the models for air to ventilate in the systems. And the fans will the fans will be the main components to keep the air ventilates in the systems. So let's go into understanding some of the assignment. So which includes the heat sinks will be an aluminium materials. So the overall casings to be polymer solid bodies, plastics, and then we have components materials, connectors materials, and more materials on these systems. Then, as I mentioned earlier, we assign the inlet and outlets for the systems and the ventilations on top as well. Then we have fans, internal fans, assigning internal fans to the systems that keeps the ventilations. And then we have heat sources assigned to each of the components, to the particular chips here. And we can also assign by temperatures instead of heat source, 4 watts to the components again, and 60 degrees C for these particular components. So once we have done with all these assignments, in your systems you might have perforator plated or even the porous medias. So we in flow simulations, what we can do is that we can represent these directly as the parameters, and this will simplify the model's difficulties in studies. So in this case, we assign perforated plates in the systems with properties of the areas, the diameters of the holes to be 0.04 and the hole shapes to be 4, and the ratios can be by pitches, or it can be by a free area ratios. So this will represent how does the perforated plates performance in the systems. So additionally, we also assign the slots perforated on top of this. Instead of putting as actual physical geometrical elements, what we have here is that we represent it with a slots with a porous plates parameters. So again, what we do is that we assign based on the size of the plots, and then in this case we use the free area ratios. We also have the options to choose between pitches as well. And once we've done with all these assignments, then our models are ready for analysis, for solving. So when we have solved all these results, then we will look into the results of it. Okay, there's a questions that asks about 0.002 meters width. So that is the width of the slots, the slot cuts. Okay, so we have okay, let's look into this. So this is basically the parameters of the slots, parameters of the slot cuts, the size of the width, and the height of the slots, right? With hole shapes of rectangulars. All right, great. So then let's look into the results plots. I will go a little bit deeper in these examples because this is a generic examples that we would look into different without any different scenarios. We will look. First of all, we will show on the temperature plots. So of course, first of all, let me just hide the whole assemblies, and we focus on the plot itself. I'll hide away the casing. So let's look into temperature plots. So let me just call a couple of it out as well. So from different view, just hide this. So you understand that how does the temperatures build up and rises into different regions. So for these parts, the heat sinks will serve as a heat dissipation components here, and temperatures on that. We might want to look into the plane. Let's play this around. Okay, looking at how does the fans blowing away the temperatures, blowing away the heats, and to understand further on the ventilations. So we can look at these. So the air blowing the heat sinks, carrying away the heat, okay, removing it away from the casings, from the top slot holes and from the perforators on the end and the fronts to capture the fresh air from outside. So that's how does it goes by. Okay, so we might want to look into the results as well on what are the temperatures on the main chips, which is under the heat sinks. So if you look at it, this is how the temperature is being built up and eventually reaches 55 degrees C during the steady states. And then we will also look at other components. So we also look at the maximum temperature plots as well of the fluids. And how does the temperature fluctuated across the system. This is the temperatures of the overall systems, and we achieve maximums of 85. Okay, and eventually as the heat sink started to perform, then at the end of the studies we achieve 81. So however, what we have done here is mainly on steady state calculations. This is not a transient calculations. Transient calculations we will be able to achieve the calculations of actual timings. So just to do introductions of transients. So the transient studies are fall under the time dependence calculations. Alright, so this is one cases where we have internal fans. So we would like to understand how is the difference between when we use the external fans studies. So now instead of the fans attached to the PCBs, we use an external fans which attach to the casings itself. So we would like to understand how would that affect the overall cooling system as well. So let's look at the results plot. So if you look at the temperature plots again, so notice that the temperature distributions are slightly different compared to the earlier one. Okay, how does the temperatures difference? It is slightly different compared to the previous one. Okay, where most of the heats are on tops rather than on the center portions. So that is mainly the main reasons here is because of the trajectories of the flows. Okay, how does the flows ventilate across the systems? So of course, some other configurations that we can work around with is that the arrangements of the components on the PCB board, the different heatsink designs, and positioning of the fans and the size of the fans as well. So I would also like to take the opportunity here to go into understanding what kind of fan curve that requires. In flows, we already have some of the predefined fan curve data available here. So these are from different suppliers with Excel or difference or by difference fans data. So we can also always insert our own database, our fan database into it. So the properties that we will key in are mainly a couple of these, including the flow rates and so forth. Or alternatively, we can also assign it based on a fan curve, which will provide you with more accurate results and the uh, actuals performance of the fan itself. So based on the flow rates and the different pressures in this when you are using this particular fan. So next up, so let's look into the end results of the overall data. So let's look at the overall temperatures first. So the maximum temperatures in this case is a 78.5. 78.5, and the coolings are actually pretty much similar to what we have earlier when we are using for internal fans. All right, and then we will also look at another one, which is the main chip's temperatures. Okay, main chip temperatures, which now we have a slightly lower temperatures compared to the previous one. Which the previous one we have a 55. So of course, when this might be slightly difficult for you to imagine. So what we can do is that we can do some compare of the results based on the color plots of two different studies, and then when we click compares, it will capture the data from the internal studies and the external fan studies, and put it together in two plots. And from here, we'll be able to see the distributions between two of them, rather than you print screening it and putting it into Excels or PowerPoint slides to understand further. So from here, we can do a quick comparisons between both of it, and how does the temperatures plots and the heat distributions, and how effective is the heats in both systems. All right. On the left-hand side is the external fan scenarios, and the right-hand side is the internal fan scenarios. So imagine the different possibilities that you can do by repositioning the components in the boards, redesigning the using different kind of fan curve, using different kinds of heat sinks as well. So maybe the spacings, to increasing the spacings will help out in the cooling of the system as well, and so forth. So let's look at the last one, which is external fans studies with a fin heat sinks. So if you look at the flows, is that we have an internal fans calculations with achieved a 55 degree C in the system. Then we use an external fans and then we achieve a 45 degrees. So if that is not something that we want it to go further, we want the temperature to go lower. So we might use a different approach, which is changing the heat sinks. So in this case, we change the heat sinks. And let's look at the temperatures in this case. So and let's look at the main chips temperatures. So you notice that the temperatures are way higher compared to the previous one. So from here we can decide that these particular heat sinks are not suitable or not as effective as the previous cases, as the previous heat sink designs. And we can also understand on the temperature plots as well. And in this case, let's do a comparison between 3 studies. Again, cut plots 1 for each of the studies and do a comparison between them. Okay, so from here, what you have here is on what you can see here is 3 different studies of 3 different color plots. So let's look at it. So we have 83 temperatures as the reference, and we have 3 studies. The first one internal, externals, and the external with a pin design studies. So the color distributions is obviously is that the second one provide you with a with, with more effective cooling and giving you a better results. So from these 3 cases, we can basically understand and basically do some decisions of this is the best designs in the overall studies. Okay, so I have a questions here. So someone requesting that is it possible to spend more time on the setting up of the simulations, like choosing the solver, applying boundary conditions, and meshing. That particular portions requires a substantial amount of time. What I would suggest is that you can give us a call on our support helpline or send me an email, and I can share with you more of these particular informations. But however, since I have some times available, so let's look into uh, just a quick one and look at these particular boundary condition setting up. So let me just take a 5 minutes, a quick 5 minutes or to 10 minutes to explain a little bit about this. So before we start any studies, we will look into whether it is an internal or an external flow. So internal flows are suitable for electronics boxes, like these cases. External flows are mostly on the aerodynamic cases. And if you have to include the conductions in the solids, you will need to put in these particular options. And if you need to include radiations calculations, usually for HVAC cases, then we will put in here. Then if you're going to do some the transient studies, you will need to require to add in time dependence. And if you need to do some natural convections, gravitational boundary conditions need to be assigned. So rotational is for turbine blades design and so forth. So as for fluids, we have compressible fluids, non-compressible fluids, and how and adding in Newtonian liquids and so forth into the systems. As for solids, we can assign all the solids. Originally, SolidWorks comes with all these particular materials from alloys to semiconductors to be assigned. If you have the HVAC modules and the electronic cooling modules, you will have more materials to be added into the system. So then we have initial conditions, assigning of the initial conditions with the ambience and the solid parameters, right? And then computation domains, usually you do not need to do anything when you are working on internal studies. And solid materials, as I have been saying earlier, we just assign accordingly to different materials in the systems. Environment pressures to simulate the openings of the cooling, and assigning fans with different data across each of the phases which represent the fans, and heat sources. And that's pretty much on that. As for the meshings wise, uh, we you can there are a couple of ways of doing it. First way is that if you have enough computer resources, what you can do is that you can always go to the global meshes and tune using the automatic and tune it to the finest. All right. So alternatively, you can go to the manuals and controllings on different sizes or on different phases. So to determine it, usually you need to know that the smallest gaps in the systems, and putting in the gaps values and the tolerance values. So in this case, you can tune between that in different channels and different cases. But in my case, usually what I will do is that I will always assign a local meshes to small gaps in this case, small gaps in the heat sinks, or small gaps between two components. And cases like this as well, I will also assign local meshes to it. It really depends on whether your computers are able to support that kind of meshing conditions or not. So my suggestions to you is that you can always try a global meshes of 4 or 5. Try to run the studies and try to look at the flow trajectories. If the flows are flowing through nicely, or even call out the plots of the color plots and add up the streamline to understand further on whether it did go through the systems or not, to understand whether your mesh are good enough or not good enough. Okay, there are a couple of questions here. Okay, let me just answer it one by one. So to do the reverse airflows is just simple as flipping the assignments of the fans here in the systems. So one in, one out. If you just want to reverse the airflows, you just put the in to be out, out to be in. That's all. Tuning the mesh will helps out in the convergence, but tuning the mesh more for getting a more reliable results rather than getting the convergence. The convergence are related to your boundary condition setting up, including the temperatures, the heat source, the fans, and so forth. And the goal plots that you assign to serve as a reference for convergence will also help in terms of the convergence as well. So if you do not assign any goal plots or any goals, sorry, any global goal or any surface goal or solid goal, volume goal in the systems, it will take substantial amount of times because you are letting the solver itself to decide which one to be used as a reference for convergence. But if you are assigning all these goals, like for examples, in this case, let's say if my main chip need to achieve a certain temperatures, then my goal will be assigned to that particular main chips. So in this case, which is this. So when I assign these particular main chips as my goal, then when these converge, the solver will converge as well. Okay. So if you would like to know more about this, I would suggest that you call us or send me an email, and I will reply accordingly. I will not be able to do the reverse airflows because I can assign, I can do some I can show you on how do I do the reverse. Okay, so instead of picking that particular phase as the exit, I just flip these two phases around to achieve the reverse airflows. But however, to run the studies, it will take a substantial amount of time. So will not be able to do that. So sorry about that. But just for your information, if you would like to flip the airflows to be in reverse directions, you just flip these two phase selections around, then you will be able to get the boundary conditions of reverse airflows. Okay, I only have a couple of minutes to goes by, so let me just quickly end the contents. So what we have here is we're understanding the coolings of difference between the internal and external fans. So if you look at here, we have 3 studies. The first one to be the internal fans on the PCB boards, the external fans on the casing itself, and then the last one we are using the external fans since external fans have a better cooling capacities. And we change the heat sinks to simulate and to understand whether the temperatures are further being lowered down. But eventually, what we have noticed is that the second one is the best designs where it removes most of the heat, where we achieve 45 degrees Celsius on the main chips. So we have gone through the case studies of LED power supplies and electronic components. So let's quickly go to the summarize of the whole scenarios. So thermal designs involving the removal of heat of a system's surroundings. So some techniques included of conduction cooling, natural convections, radiation coolings, forced air convection cooling, liquid cooling, immersion cooling, and heat pipes. So however, not all are able to simulate, like immersion coolings are not able to simulate in flow simulations, but however, most of the cooling techniques that commonly applied in the industries are able to be simulated with flow simulations. So with CFDs, you allow you to predict any failure modes in the early stage of the design process. The iterations including boundary conditions iterations or including the geometrical iterations. So this will definitely help you to make decisions better and faster before your actual prototyping and getting the actual testing results. So so that pretty much on the contents of the webinars. We will be sending out a survey forms. We'll be sending out survey forms to you. Please fill it up and let us know how we can improve on the webinars. And there are some social medias. This is our social medias ads. So feel free to add us. So to get more updates on what are the activities and events that we are planning across the years and periods. So and then on the right bottom corners I have that is my email address. So if you have any questions or there are things that I did not manage to answer today, so please feel free to drop me descriptions and any questions, and I will be replying accordingly. So do leave us, when you are sending me email, do leave me the contact number as well, so that we'll be able to call you up if there are any things that I do not understand. Alright, so that pretty much on today's sessions. So I have